Today we are going to discuss about fundamental theorem of calculus. It is a very important theorem because it connects differential calculus with integral calculus. Now what is this fundamental theorem? Suppose I have been given a curve like this. This is y is equal to fx or y is equal to ft is the curve I have been given, and I start finding area under this curve from say x is equal to a to any given x. And let's say that okay, this area function is given as area is equal to fx. So this is my area function. Now this area function given denoted by capital Fx. Now this is a function of x, this x. Why this is a function of x? Because as I change my x, suppose I decrease my x, then this area function fx will decrease. If I increase my x, then this area function fx will increase. So this is a function of this x. And this function is defined as fx is equal to integral a to x ft dt. That is, it is integral of this integrand from lower limit a, that is from here to x. And why this is defined like this? Because I am calculating my area capital Fx from x is equal to a to this particular any generic value of x. Now this is a function that I have defined. What else can you say about this function? Whether it will be a continuous function? Let's see. For continuous function, what I have to do? I have to take the limit h tending to 0 and see whether fx plus h is same as fx. So I will have to define, I will have to write fx plus h. So this will be integral a to x plus h ft dt. Now what will be my f of x plus h minus f of x? That will be integration from, if you do this minus, it will be very simple, it will become here x to x plus h integral ft dt. So as limit h tends to 0, what will be this f of x plus h minus fx? This limit will be x to x. So integration of any function, any arbitrary function, say from a value x to another value x, that is what? It is an integration over zero width interval. So this ft dt will be equal to 0 for any arbitrary value of this function. So what I can say, that limit h tending to 0, f of x plus h minus f of x will be 0. So I can write limit h tends to 0, f of x plus h is equal to f of x. Now what is this definition? This is definition of a continuous function, because as h tends to 0, f of x plus h is equal to f of x. So therefore what I have proved, that this area function defined like this, that fx is equal to integral a to x ft dt, is a continuous function for any kind of ft. I have not, in this diagram it looks like a continuous and very smooth and nice function, but if even if this function is discontinuous or it has got some points where it is not differentiable, even then this capital Fx will be a continuous function. Okay, only assumption I have taken, that okay, this ft somehow I should be able to integrate, that this is an integrable function. Okay, now that I have proved that this fx is a continuous function, let's check whether this is a differentiable function also or not. Now for differentiability, I will have to take limit h tends to 0 and then find the differential coefficient. So basically I have to do something like this. This is f of x plus h minus fx I will have to find out, and f prime x will be limit h tends to 0, f of x plus h minus fx divided by h. In last calculation, in last derivation, I had shown that what is this f of x plus h minus f of x is basically this integral, this red portion, because it is the area under the curve from x to x plus h. Okay, now this will be approximately equal to h of x. If my h is very very small, then although this is a curve, this y is equal to ft is a curve, but I can approximate this area with area of this rectangle having width fx having height fx and width as h. So this area, that is f of x plus h minus f of x, will be approximately equal to h of fx. So this approximation will be exact when I take this limit h tends to 0. So I can write f prime x is equal to limit h tends to 0 f of x plus h minus fx divided by h, that will be is equal to fx. So let's give a rigorous proof of this theorem, that f prime x is equal to fx, and what are the conditions under which this f prime x will be equal to fx. So that theorem is called fundamental theorem of calculus, and it is as follows. Let f be integrable on a b. This is my closed interval a b. Now see, I have just used the condition that f is an integrable function. I have not said that f is continuous or f is differentiable, nothing. It may be that my function may not be continuous also. Even then, f may be an integrable function. I will come to this point later in my slide. So what I have taken, that let f be integrable on ab for a less than equal to x less than b, and let fx is equal to integral a to x ft dt. So this is my integral, this is my area function. Now then f is continuous on ab. This I have proved earlier कि no matter what kind of function f you take, this capital F, that is the area function, has to be continuous. Okay, now comes the second part. If your f, the small f, this curve, if it is continuous at x, then f is differentiable at x, that is f prime x is equal to d by dx integral a to x ft dt will be fx. So this fundamental theorem of calculus, you can break it into two parts. First part, it says that no matter what may be my this ft dt, this function will be a continuous function. Okay, part 1 over. Part 2 says कि if in addition you put a condition that this f, this small f, is a continuous function, then you will get a f as a differentiable function, and this f prime x will be fx. Now let's derive this theorem. So f prime x will be limit h tending to 0 fx plus h minus fx by h. I had shown in earlier slide also. So this will be limit h tends to 0 1 by h integration a to x plus h minus integration a to x. So this will be integration x to x plus h ft dt. Now I have to find out what will be the value of this integral from limits x to x plus h. For that I will use a very simple theorem of definite integral, and that theorem is max mean inequality or anything. Suppose you have been given any arbitrary function y is equal to fx, and in this interval say a to b, this is the minimum value, the green line is the minimum value of f, and the yellow line is the maximum value of f. Now this integral from a to b will be area, and that exact area will be this blue one. But this area, the exact area blue one, will have a lower bound this, because this is my lower approximation, and will have a higher bound this yellow one, because this is the higher approximation or the upper approximation of this area. You can just write it as that minimum of f into b minus a will be less than or equal to a to b fx dx. This will be less than maximum value of f into b minus a. So minimum, let's take this minimum as small m. So small m into h. Now I am working, instead of a to b, I am working from x to x plus h. So the width of this interval is h. So this b minus a will become h. So m into h is less than x to x plus h ft dt less than capital M h. Now I divide everything by h. I will get m is less than 1 by h, x to x plus h ft dt is less than m. Okay. Till this point it's very clear. Now use the extra condition which I have given, that f is a continuous function. Now the moment if f is a continuous function, now what is this thing? This thing is a number lying between lower bound and upper bound of a continuous function. So the intermediate value theorem for continuous function, what did it say? You give me any lower bound and upper bound of a continuous function, then there must be a number c, so that fc will be equal to this thing, that is the function assumes each and every value lying between m, small m and capital M. So this number must be obtained by one of the c. So this number must be equal to fc. So that's what I have written. This intermediate value theorem says that 1 by h integral x to x plus h ft dt will be fc. Now you see, I had shown in last slide that f prime x is equal to this thing. I can write this 1 by h whole thing as fc. So this is now limit h tends to 0 fc. Now you see f is continuous at x. So fc approaches fx. Why? Because your c is lying between, your c lies between x and x plus h. Okay, c in this interval. So in this interval x to x plus h, there is a fc and there is fc, such that this fc is equal to this thing. Now as your limit h tends to 0, this interval shrinks. So ultimately this c will be equal to this x. So this limit h tends to 0, fc will be equal to fx. So I have proved that f prime x is equal to fx. Now this proof must be looking very daunting and intimidating to you, but this is because I have used it in technical mathematical jargon and mathematical terms. But the basic idea of this proof I had shown in the very first slide. And what was that basic idea? That basic idea was that when I have to find f prime x, I take a very small interval. That area of this small interval can be approximated as the area of the rectangle. Area of the rectangle will be this height fx, this width h of x. When I divide this area by h, I get fx. Okay, so this is the proof of fundamental theorem of calculus. Now let's see, I had used this condition of continuity, and why this condition is so important. Suppose I take a discontinuous kind of function. Okay, now first of all, can this function be integrated, say from limit say 0 to I am taking say 5? Can I find something like 0 to 5 integral of this fx dx? The answer is yes. Yes, the answer is yes. For a function to be integrable, continuity is not important. So even if this function is discontinuous, I can integrate it. But discontinuous in what way, that I will come. So let f be integrable on a and b, then f is continuous on a to b, and if f is continuous at x, then f is differentiable. Okay, so let me give you the condition of integrability also. This function I can integrate. So although this function has discontinuity, I can integrate, and so only condition is that this number of points where this function fx is discontinuous, that those number of points should be finite. For example, if I have to integrate my function say from 0 to 5, I can have say 10 or 20 or 1000 or 10,000 points at which this function is discontinuous. So number one condition is the number of points at which this function is discontinuous should be finite. Okay, number of discontinuities should be finite. Second condition is this continuity, that is this jump also should be finite. That is from here from 3 to 6 or 3 to 3000, it should be a finite jump. Then only I can integrate my function. You cannot have a function something like this. If I give you a function fx is equal to 1 minus say x minus 1 whole square. So this function will be what? X will be 1 here, this will blow up like this. This will be my function fx is equal to 1 minus 1 divided by x minus 1 whole square. This function, if you try to integrate say from 0 to 5 or 0 to 10, you cannot, and you will go into the realm and the domain of improper integrals. Then you will have to use certain tricks to integrate it. So as long as the number of points of the function where it is discontinuous is finite, and as long as this discontinuity is also finite, that is this jump is finite, I can integrate any function. So these kind of functions are also called piecewise continuous. Piecewise continuous meaning they are continuous in different pieces. Like you see, from here to here it is continuous, then again from here to here it is continuous. So such functions are called piecewise continuous function. This function which blows up, which goes to infinity at x is equal to 1, it will be very difficult to integrate it, and we will have to use certain other methods. Now once I have found that okay, this is the condition for the function to be integrable. Now what happens, actually you see, when you integrate this function, what happens that the integral will be something like this. Why? Because this area is increasing, this is 3 and 4, so area will be increasing, but before 4 the area will be increasing at the rate of 3, but after 4 the area will be increasing at the rate of 6. So there is a what you call corner point here, and at this corner point my function is not differentiable. So once again, when I take a discontinuous function, I can integrate it, but suppose this is my point of discontinuity, that is 4 is my point of discontinuity. Before 4, what is the derivative? The fx, the derivative of this function is 3, so it is increasing at the rate of 3. After this point of discontinuity, that is after 4, it is increasing at the rate of 6. So this function will be not differentiable at this place. That's why in fundamental theorem of calculus we say that this is a basic condition, that your integrand function, the small fx, should be continuous. Then only I can have a differentiable fx, and I can differentiate fx is equal to this. Okay. Now once again I will show you what this integration is doing. I had shown you in last slide that once I integrate a function, suppose I integrate this discontinuous function, I get a continuous function. Although this function is not differentiable, but at least one, you can say, bad property of this function, that it was discontinuous, that has been removed by the integration operator. This integration is a purifier kind of thing. It purifies the bad properties of a function. So I will show you once again. Suppose I give you a not continuous function. This is a not continuous function. The moment you put this not continuous function in this integrated box, after integration it will become continuous. So it has purified one bad property, it has removed one bad property of this function, this fx, that it was not continuous. Although it has not removed the second bad property, that it was not differentiable also. Obviously if a function is not continuous, it will not be differentiable. So this final product, the output, I am getting fx, although it is continuous but not differentiable, but at least it has removed one bad property of this function. So this, you see, this function is continuous, but it is not differentiable at this point. Once you put up this function as input to this integrator, you will get a function something like this. So it will be continuous also and differentiable also. So this integrator removes the bad properties of a function. If it is not continuous, it will make them continuous. If it is not differentiable, then it will make them differentiable.